Okay, so most of the videos I've made so far have dealt with complex algebra, more or less. But we haven't really addressed kind of the analysis part of complex analysis, the calculus part of complex analysis. And there's two portions to that. There's, taking derivatives, and there's taking integrals. And we're going to do derivatives first. And the first thing I want to do is really kind of unify our entire conversation about derivatives and complex derivatives in one big theorem that I'm going to call the fundamental theorem of complex analysis. I'm not the first person. I know of at least one book that refers to it as this, but at the same time, I'll admit this isn't a phrase you're going to hear very often, fundamental theorem of complex analysis. But I think it's great because it unifies the whole spirit of at least the derivative aspect of what complex analysis is supposed to be. So let me just explain roughly what this fundamental theorem of complex analysis is, and then the next several videos are going to be spent basically discussing and proving it. So here, f is essentially a function from complex numbers to complex numbers. It's not absolutely mandatory that it be defined on the entire set of complex numbers, but in general, we'll just say that it's a function of complex numbers to complex numbers, and we'll write it as u plus iv, where u and v are mappings from the complex numbers to the real numbers. So I mean, right, any complex number in the range, this is supposed to give numbers like x plus iy mapped to some u of x comma y plus I times v of x comma y. So in particular, these are mappings from R2 or some open subset of R2 to itself. And we kind of already saw and discussed some aspects of that before when we were looking at the specific case of f, multiplication by some fixed complex number or something. Okay. So the fundamental theorem of complex analysis basically lists several different properties that a function from the complex numbers to itself might have, and tells us that in certain circumstances they're all kind of equivalent to one another, which is actually surprising because they're pretty different properties. And what you'll find is, well, let me actually jump right in. The first property that we're discussing is complex differentiability at every point A in the domain. So complex differentiability, I mean, remember, real differentiability means that this limit exists. The limit of this Newton quotient, f of a plus h minus f of a all over h, as h goes to 0, exists. Except, now what happens if we interpret a and h and the function f not to be real numbers, but rather to be complex numbers? You can still divide by non-zero complex numbers, you can still subtract it, etc. It all makes sense. So you can just define this in the case of complex numbers, and this gives us a notion of complex differentiability. That's probably the most obvious property we have, and if it exists for each a in C, we give it a name, a special name. We call this functions holomorphic. So that's a word you're going to hear a lot in this context. But holomorphic essentially means complex differentiable at every point in the domain. Alright, so this should sound similar to basic calculus. We had real functions mapping real numbers to real numbers, and we asked that they be differentiable in the traditional real sense. Is complex differentiability really that different than real differentiability? Well, it turns out the answer is yes. So one of the themes I'm going to try and bring out is not just that we have all of these equivalent notions of complex differentiability or holomorphicity, but I also want you to pay close attention to, these complex differentiable functions all obey these properties. Do real differentiable functions obey these properties? And for the most part, the answer is a strong no. This condition of complex differentiability, and we'll discuss why later on, but it's incredibly rigid. I mean, it's very hard for a function to obey complex differentiability, but it's, by comparison, pretty easy for it to obey real differentiability. If we were dealing with real analysis instead of complex analysis. So these things are genuinely different, and that gives complex analysis a very different flavor than real analysis. It makes the subject a lot more rigid and quite frankly a lot more interesting. So what are some of these equivalent properties that a complex differentiable function or a holomorphic function will obey? Well, there's the Cauchy-Riemann equations. I mean, like I said before, you have a mapping of R2 to R2. You can think of it as u of x comma y comma v of x comma y. So if we like, you can think of it like this: u of x comma y comma v of x comma y. But not any mapping of complex numbers to itself is going to obey complex differentiability. And it turns out that, as we'll see, if you're complex differentiable, if this limit exists, then we have the Cauchy-Riemann equations. The partial of u with respect to y will actually equal negative the partial v with respect to x. And there's other relation too. There's another relation too. But the point of these Cauchy-Riemann equations is going to have something to do with that kind of mysterious thing that I tried to make a little less mysterious. There's a relationship between complex numbers a plus ib and matrices of the form a negative b, b a, just like this. So we've been talking about that a little bit, and that's really going to be the whole spirit of Cauchy-Riemann equations and what makes them so interesting. That means that the Jacobian matrix, and I'll explain this in greater detail later, but the Jacobian matrix, or the matrix of partial derivatives of this function from R2 to R2, had better be of this form. And we've seen that linear maps that are of this form actually have some very nice properties. So remember, they're elements of something I call GL1C, and you can see that video later. So that's something to discuss later, but it already shows us that it kind of, the complex differentiability forces us to respect complex linear algebra at some level. Then there's Cauchy's theorem, and to really explain this, I kind of have to give you an idea of what the integration is going to be. When you integrate a complex function, you integrate it not over a region, but we're primarily interested in contour integrals, where you kind of do a line integral around some line. And so the point is that if f is differentiable at every point in the interior of this region, then when you integrate around this contour, you get 0. That's Cauchy's theorem for any simple closed curve C, and we'll address that later on. It's a very interesting and powerful theorem that relates complex analysis to topology. And you can be a bit more precise here. You can actually look at Cauchy's integral formula. This is also a really interesting theorem. It tells us that if you want to know the value of a function at a point, and the function happens to be complex differentiable in a region, or holomorphic in a region, then all you have to do is integrate not that function, but this function divided by z minus that point of interest. So I've already drawn it here, where C is, say, a circle going around this point, centered at this point. If you do a little contour integral around it, and you're not integrating the function, of course, remember, integrating the function will give you 0, but if you integrate the function divided by z minus a, then that'll actually give you that value of the function at that point. That's very interesting. Up to a factor of 1 over 2 pi I. And I should just mention very quickly that, of course, I know I haven't defined anything rigorously, but of course f of z over z minus a isn't going to be differentiable at a because it's not even defined at a. You can't divide by 0. But Cauchy's integral formula it's very interesting. I mean, it's telling you there's a lot of rigidity, that you can already predict the value of the function at this point if you just know what its value is on some circle centered at that point. That's very loose information. That should remind you of if you have a linear function and I tell you what the point, what its value is at 2, and I tell you what its value is at 4, then you should be able to figure out the entire equation of the line. And that's essentially what's going on here. In particular, you should be able to find its value at 3, exactly dead center. So, I mean, linear functions, those are incredibly rigid. And yet, this is kind of coming from the idea that holomorphicity, complex differentiability, is really quite rigid. I mean, it's almost as rigid as linearity of just a regular function. Another interesting thing about these things is, we haven't been graphing complex functions because we can't visualize 4 dimensions, but we've been interpreting these complex functions as transformations of the plane. So remember, multiplying by a fixed number r e to the I theta scales by r, rotates by theta. Or conjugating, it flips it over the real axis. It reflects the entire complex plane through the real axis. And then we also discussed inversion in the unit circle, right? 1 over z bar, which kind of swaps the interior of the circle with the exterior of the circle. Of course, it's not defined at 0, but That's not a big deal. So it's nice to think of these transformations as manipulating the plane you're in instead of trying to graph it. And if you think of it that way, the function actually is, if it's differentiable everywhere, it's actually angle preserving, and that has a lot to do with the fact that it respects complex linear algebra, as we'll see. So the word for that is conformal, but I don't want to get too much into the details here, but it kind of preserves angles, so that if you had two curves in the complex plane that made a certain angle with each other, when you apply a holomorphic mapping to them, it'll alter them, In fact, one of them might even turn straight or something like that. But the angle between them actually stays the same. So that's interesting. Another thing is that U is harmonic. It obeys this nice little kind of partial differential equation. If you take the double derivative of, so U, what is U, first of all? Remember, U is the real part of this mapping from R2 to R2. It's the first component. And the same thing holds for the second component. There's nothing special about U. But it obeys this nice little Laplace equation. So you probably haven't studied a lot of partial differential equations, so this doesn't mean much to you, but this is actually the heart of a lot of these other properties. Things that are harmonic, things that obey this equation, also obey a lot of these other theorems and properties up here. So that's kind of the whole spirit of it, that it obeys this equation. And, just to whet your appetite, this is the equation, for example, that you would expect electromagnetic fields to obey and gravitational fields to obey and so on. So this is actually very fundamental to the theory of partial differential equations, physics, engineering, and plenty of other parts of mathematics. And then finally, F is complex analytic. So remember, real analytic means that you can be expressed as a convergent power series, where I think if I recall, the formula is the nth derivative at the point A over n factorial times x minus a to the n. And the goal is we want that to equal f of x. So you expand it as a power series around a point. I reviewed this a little bit when I was discussing the proof of Euler's formula, so you can go back and watch that video. And in particular, I mentioned that not every function has one. It's actually, think about what this is saying. This is saying that you're kind of like an infinite polynomial. So that's the great thing about real polynomial. That's the great thing about real analytic functions, functions that really can be expressed as these power series. They're infinite polynomials. They have a lot of the properties of polynomials. Of course, things get a little tricky because there's an infinite number of terms that can complicate things, but still, there are a lot of theorems you can prove about them that are similar to theorems you could have proven for polynomials. And what this is saying is that if you're complex differentiable, even just one derivative, you actually can take the derivative infinitely many times, and you can put them in a power series, and that power series will converge to the original point. That's incredibly rigid, and we'll talk about that a lot more later on. But this is really surprising, and it means that these complex differentiable functions are kind of like infinite polynomials. And that's going to be another theme that kind of emerges. So they're infinite polynomials, they obey Laplace's equation, which, if you only knew how powerful that was. Cute little fact, they preserve angles. Some interesting and powerful theorems that are going to be very useful for us. Cauchy's two major theorems here tell us how to handle it. The fact that they obey Cauchy-Riemann equations means that they respect complex linear algebra in a certain sense, which is kind of the reason for all these things happening. Complex differentiability. So this is actually a very beautiful theorem. It's an incredibly beautiful subject. So again, some of the dominant themes we're going to pay attention to is, how does this look like an infinite polynomial? And how does this all differ from the case of real differentiable functions? So, and in general, we're just going to try and prove all of these qualities.